Hello, this is Sadhvi Varagur Karthikeyan. I'm going to be discussing about subband image transmission reception over CDMA link. This is a project for wireless communication EEL 6509 done as part of my master's at University of Florida Spring 2016. Now I'm going to be discussing about the motivation behind this project. Image and video transfer and sharing have been the major constituents of multimedia transmission over cellular networks as well as PCs. Data sharing is restricted by the limited spectrum available, which in turn restricts the number of users on the channel. Code division multiple access offers a unique scheme of orthogonal codes in order to tackle this problem. In addition, present-day CDMA wideband signal carrier permit enhanced image quality by superposing different signature codes over divided image information. CDMA also enables access to more than one image information simultaneously, with no delay on a given channel bandwidth. This project aims to effectively evaluate the problem described above and give a unique implementation for image transmission over CDMA channel. Now coming to the overview behind this project, there is significant interference involved in every communication channel. The combining or repelling effect between the two electromagnetic wave carriers is what causes interference. CDMA, however, ensures reliability by means of its block level coding scheme shown in figure 2. We can see that from the block level system, the noise at the receiver end is easily filtered out, thereby giving us the reconstructed original image. Now, talking about the application of image transmission application over CDMA, there is a block diagram given in figure 4. This block diagram is a typical CDMA system for image transmission. It shows a number of image information on different channels being spreaded and transmitted via a single antenna. The receiver takes in this information, which is then despreaded and assembled to obtain the original picture. In case of color image, we have an extra code to calculate the luminescence and chrominescence value shown below. Introduction to CDMA. CDMA-based spread spectrum technique is often also referred to as white noise transmission. The input data is XORed with the chip or the spectrum code to get an output data stream which has a higher data rate. This chip is then reused at the receiver end to generate the original data. A simple block diagram shows the actual set of operations at the receiver and transmitter end. So as we can see, data is a 5-bit data here, and the unique code is individually XORed with every bit. Thereby the spreaded code is a wider bandwidth code. Now at the receiver end, this despreaded code is again compressed and decoded to obtain the original bits of ones and zeros. Pseudo-random generator. A linear feedback shift register is the one that constitutes a pseudo-random generator. that has a dedicated sequence but produces values whose cross correlation closely resembles that of a random generator. Hence the name pseudo-random generator. The number of taps indicate the unique output. The number of bits give the maximum number of random values possible, after which the sequence tends to repeat. The range is dictated by 2 power n minus 1. This is also defined as the length of the Pn sequence code. Each pseudo-random sequence can be uniquely depicted with a polynomial. The polynomial representing a 5-bit LFSR is shown in figure 6. This pseudo-random generator is the one which is being used to generate our goal code. Pseudo-random generator has a set of properties. The Pn sequence generator has unique properties that confirm their cross correlation with that of a normal random generator. Property 1. The balance property. The number of ones and zeros in the Pn code should only be different by 1. Property 2. Run property. The following 4 categories of ones or zeros run property that define and verify this property are the half run, the 1/4 runs, and the 1/8 runs. Correlation property. The correlation between two Pn sequences can be obtained by counting the number of same and different bits. These properties are very important while creation of a goal code. Implementation stages. The project was taken through the following stages: reading image file and generating the desired spectrum codes, XORing the generated goal code with the binary image matrix, image transmission socket code, image reception socket code, and despreading the code at the receiver end. The coding was done in MATLAB. So we take up the desired image, which is first read and then converted to a binary image in case it is a colored image. This gives us a binary vector. The goal code is similarly generated from a random generator as shown. Now the given code is XORed with the binary matrix to get the spreaded code. The immediate matrix dimension increase is similar to spreading of data over a larger bandwidth as in conventional CDMA. Image transmission socket code. This code enables us to send our spreaded code from our port to another computer. The spreaded code is returned to an image file called the spreadedimage.png, and it is sent to the receiver via the TCP/IP protocol wirelessly. This involves the use of a Java code to transmit the desired information to another computer, which is the receiver. Not only this, we also send the goal code as part of a text file via this port. Concept behind socket programming. Figure 7 shows that for a communication link to be established, we need to create socket objects and join them to the server-side sockets. As can be seen from the figure, the socket A0 accepts the request from socket B0, which is the client. The next step is for the server side to create a socket, which in our case is socket A1. Now the connection is established. Image reception using the socket code. So as part of the MATLAB code, the spreaded image is read and the loaded file is received, which contains the goal code. The goal code to the desired channel is being sent using the receive.txt file. Hence, only if the user at the receiver end has this can he produce the original image. Despreading at the receiver end. At the receiver end, the following code segment despreads the obtained code to reconstruct the original image. The goal code accessed by the receiver is like the key to the access of the desired channel. These are some results obtained from our experiment. We have done this for over 3 image files, and this is the output for one image file. As can be seen, the transmitted image file is first binary converted and it's reconstructed using the despreaded code at the receiver end to obtain the original image.